Good evening. I appreciate the opportunity to spend a little time with you and go over some things that I've found to be very interesting. If you're like, I think many of you here are like me, you spent too many years in school. And one of the things that happens in school is we learn that science is the final decider of what's true and what is not true. Anything you can measure, anything you can predict from, becomes the final arbiter of truth and doesn't really let anything else in. And we're going to find out tonight if there's any limitations to that type of worldview. And for tonight, I can be Gary. I'm not at work, okay? But we're happy to spend this time with you tonight to look at religion versus reality and see if science really describes a version of reality that stands up to what the evidence actually is. I like to read bumper stickers, and one of the ones that we see sometimes is question authority. And that's what a skeptic does. And our job tonight is to find meaning in an age of skepticism. And one thing that is true, I think, of the human condition is that as we live our lives, there are certain questions that we have to answer. And whether we choose to write them down on a pad and pencil and actually skull out an answer, that is, think it through, the decisions we make actually help define the way we've looked at our worldview. For instance, a question like, who am I? Our identity. Where did I come from? Our origins. Why am I here? Our purpose. And where am I going? Destiny. The decisions we make in our lives define how we've answered those questions, whether we've actually thought about it or not. When we roll out of bed and start making decisions, our worldview is answered in the way we make those decisions. Tonight, I'd like to focus on one of these questions because I believe we can get a handle on these four very important questions by looking at where did we come from, our origins. Because if we knew where we came from, we'd be able to get a grip then on who am I, why am I here, and where am I going. Without knowing where we came from, we really don't have a place to start in order to answer these very important questions. When we look at origins, or where we came from, that branch of science is called cosmology. Basically, if you boil all the cosmologies down, there are two basic flavors out there. The first one is that the universe has always existed. We can summarize it a little bit like this in this diagram, the vertical bar demonstrating a point in time where all available evidence from every discipline of science indicates that the universe is running down. The amount of usable energy present in our that we can measure in every closed or open system shows that there was a discrete point in time when the universe had to begin. It could not have always been here. What's the point of that? The point is that we don't have infinite time backwards. The universe has not always been here. I'm not here tonight to tell you how old the universe is, but I can tell you that all available lines of evidence point towards a discrete point in time when it started. We do not have infinite time backwards. Try to remember that. That'll be important as we go further into tonight's discussion. So, we know that the universe had a beginning. But was that beginning something that happened spontaneously, by chance, or by necessity? Or was there a design, or some first mover, or prime mover, as some people have put it, that caused it to be and set it into motion? One of the things or two of the terms that I think we will not be discussing tonight is evolution and creation. Why do I say that? Because when we say evolution or creation, those terms come with a lot of baggage that can obscure the actual points that we need to look at today. The key element behind evolution, as it's commonly taught and understood today, is that chance and undirected processes are all that are present or necessary in order to explain the world around us. Whereas creation, or someone who believes in creation, would believe that there's direction or design or a prime mover, something that got things started in a non-random way. Naturalism is chance plus time. Design, then, is direction, a prime mover. These are the two opposing things. Rather than creation and evolution, I believe a defining term for us should be naturalism and design, and this is what we'll discuss tonight. Can we detect design in nature? Any rock climbers here tonight? Oh, I see one. There's a brave one right here. Very good. Do you know where this is? Okay. This is in Oregon, okay? I'm not actually a rock climber, but my wife Cheryl is. So we're driving out down to Smith Rock near Bend, and it's a great place to climb rocks, I understand. So we're driving down there, we turn the corner, and we see this rock formation. And I'm stunned. Look at that, Cheryl. I hit the brakes, and I say, time for you to get out of the car, climb up there so I can get your picture. See her there on the side? And she's pretty good at that. So I take her picture, and she clambers back to the car, and I said, look at that picture, okay? Isn't it amazing that the wind and the rain through thousands and millions of years have blown down the canyon and made this rock look like what does it look like? A cobra, a monkey's head, doesn't it? It's called monkey's head rock, okay? So we're happy with that. Cheryl buys that explanation. We keep driving east. We get on 84 and we go all the way to South Dakota. And we turn the corner because, and I see another rock formation. I'm so impressed, I hit the brakes and make her climb up again. Cheryl, you got to climb up there because I want to get your picture with this. Look what the wind and the rain over thousands and millions of years did to the rock on the mountain. Because look, it looks a lot like Washington. It looks a lot like Jefferson, Roosevelt, and Lincoln. But it's amazing what the wind and the rain can do over a long period of time. Now you laugh because we intuitively know when we see design, don't we? Or we think we do. But maybe we can fine-tune that a little bit more and look for compelling evidence of design in my field, which is biology. And I'll ask you to bear with me as we take a whirlwind tour through a naturalist view of origins from a biological perspective. Because understanding a few of the basics of molecular biology is important in order to understand why I'm interested in looking at this in terms of design. So, the bottom line for naturalism, let's look at a few of the bedrock principles of naturalism. Life arose by undirected processes, chance. And given enough time, chance over time can cause even the improbable or almost unreasonable to become possible. All you need is enough time. Now remember, we don't have infinite time backwards. At the outside, we have maybe 15 billion years. About is the longest that we can have evidence for. But we don't have infinite time. So in a finite amount of time, even the improbable becomes possible with chance. Now, chance plus time is all there is. These are sufficient causes to explain the origins of life. Chance alone is the source of every innovation of all creation in the biosphere. Pure chance, absolutely free but blind, okay, is at the very root of evolution. Nature with a small n is all that we have, not nature with a big N. There is no personality in nature. It just is. There's no should-bes. It just is a brute given. That's all that there is. So let's apply this to a biological theory. And I'll beg your indulgence here and try to follow along because we'll connect the dots very shortly. Current theory of origins, naturalism, states that at some point in the Earth's past, there was something called a prebiotic soup. Biotic means life. So before there was life, there was this soup. And in this soup, there's the building blocks of life, okay? Like those. They look just like that. And they bounce into each other in a random manner, and they exist in order to form structures that are important for life. So these are the building blocks. Initially, there was something called amino acids. If we add ammonia, methane, and hydrogen gas together, which is what was postulated to exist in the early Earth. And we know that there are lightning bolts and there are volcanoes, so we can heat this solution and put some electricity through it. If we catch the resulting mixture into a water trap and separate out the components when we want them, we can get a few of the building blocks of life, that is, these amino acids. And there won't be a quiz on this, but this is what they look like. These are the 20 amino acids, or 20 or so amino acids, that make up the proteins in your body and mine, okay? And these are just building blocks, so we don't care about the names right now. Just know that these are building blocks of life. Alone by themselves, the amino acids don't do anything. They have to be strung together. So first they make short little words like this. But a protein is a group of these amino acids strung together, more like that. A small protein may be 100 amino acids or so, strung together like a little train hooked together. And so the red letters you see here, it says CN, CN, CN through the middle, is actually the backbone of a protein. And each of the building blocks has unique chemical properties that allow it to give the protein its structure and function, and it's solely dependent on the order in which these blocks are put together. Okay, so we have a nice little chain here. The diagram on your left is a ribonuclease, which is an enzyme that's necessary to cause replication or reproduction of your genetic material. So you can't live without this enzyme you see up there. It's 129 building blocks long. That's small for a protein. When you put these building blocks together, the side chains off the backbone give the protein a three-dimensional structure, and you can see it across the bottom here. That three-dimensional structure gives the protein some metabolic activity, or it may or may not. It turns out it's very specific. They only do one particular job or set of jobs. This is what it looks like in 3 dimensions. You can see that its three-dimensional shape exactly fits the shape of the chemicals that it's trying to do its work on. Every protein has a specific job, and it's dependent on the order of the little building blocks it's made out of. So, if you have a protein that does work, then you can start having a metabolic pathway, okay? These metabolic pathways composed of these proteins are a lot of information because you have to remember how the protein's made. You have to get the order of those building blocks set together. In order to maintain that information, the code has to be stored on genetic material, which is your DNA. You read a lot about DNA and the genome, okay? You see it on CNN, Time magazine. The DNA is actually a lot like a protein in some ways because it's made up of 4 building blocks. We won't go into the details except to say the 4 little building blocks are arranged down this zipper-like strand attached next to each other, and the 2 strands then protect themselves by connecting so that the base pairs, that is the building blocks of the genetic material, can protect each other. It looks something like this when it's done. So the little ladder-like things going up and down are actually little bits of code. You have 4 possibilities. The order in which you put those 4 bits stores the information for all the structural proteins in your body, okay? And your DNA and my DNA, I think we're pretty close, has about 5.5 billion of these little base pairs, okay? It's about as many letters in Encyclopedia Britannica. And this is what it looks like in 3 dimensions.
This is the DNA double helix. The carbon atoms are shown in black, hydrogen white, oxygen red, phosphorus yellow, and nitrogen blue. The sugar phosphate backbones are easy to spot by the yellow phosphorus atoms. The bases are stacked in the center of the helix. You can see a narrow and a wide groove running up the molecule. The wider one is the major groove. Some proteins can read the base sequence by binding and inspecting the major and minor grooves. The DNA strands are antiparallel. They run in opposite directions.
So all of the information for the proteins that make up your body, the sequence of the amino acids gives them their character, their structure, their 3-dimensional shape, their biological activity, and all that information is stored in the DNA. It has to be in the DNA first, and then the proteins are made. We'll show you more about that later. Because when you have the DNA here, now we have to get to life. So it has to be in a cell with a membrane that is something that separates the life from the non-life, and you've got genetic material. When you have metabolic pathways with a way to reproduce it, then you have simple life. And from simple life, we're told, comes you and I, or complex life. So let's go back to our original question. Now that you understand biochemistry, I saved you a graduate course. Is design detectable in nature? Are there some criteria we can use to try to separate Monkey Head Rock from Mount Rushmore? And it turns out that there are. And one of the hallmarks of design is something called complex and specific information. In the human experience, the only source of complex, specific information is some intelligent input. It does not occur by chance. So this is a hallmark of design, something that separates us, Mount Rushmore from Monkey Head Rock. And let's illustrate this way. We've got a cat at home. His name's Esau. And he plays Scrabble, where he pushes the little pieces with his nose. So we're going to see if Esau is going to meet our criteria for complex and specific design or not. Okay, Esau, go to work. How many people think Esau could have done that? Yeah, Esau did that, okay? It's actually a very complex group of letters, isn't it? Because it would be difficult for you or I to reproduce it. And it's very specific as well, but it carries no information. So we give Esau another chance. We come back 5 minutes later, he's done this. There's some information here. There's a message in these letters. But it's not very complex, is it? We could think that chance might have done that. Esau might have done that, right? Now suppose the letters were magnetized, just like an amino acid is, in such a manner that they tend to hook themselves together in little bits, and little coherent bits. And this gives Esau a chance maybe to earn his supper. And the letters are arranged like this now on the kitchen floor. They're stuck together and they've got this sequence. It's fairly complex, 25 letters, 4 spaces. It's pretty specific, but it carries no information. Okay, Esau, you're not making it. We'll give you one more chance. We go back in there. 5 minutes later, the letters are like that. Now, what are the chances that Esau did this? Anybody think Esau did it? It turns out mathematically you can look at what the probabilities are. And this is what is done in information theory. Because if we look at this statement is an accident. It's a 29-member sequence, okay? 25 letters, 4 spaces, and there's 27 possibilities per letter, right? 26 letters plus 1 space. So if we spin the dial like the prebiotic soup, trying to hook the amino acids one after the other, about 20 in each group, right? About 20 possibilities, we hook them together. We have a 29-member sequence, like a very small protein, okay? Now, is this a very likely thing or a very unlikely thing in order to get this specific sequence, which is what you need for a biologically active protein, right? You can't get almost, it has to be just right. What are the chances that this occurred without help? That number. Okay, that's a really little number. I have trouble getting my hands around that, okay? 3 times 10 to the negative 41, that's really little. Well, let's imagine like this. I take a healthy volunteer from here, blindfold you, and push you out of an airplane with a parachute over the Sahara Desert. I've told you that ahead of time, I've painted 1 grain of sand red in the Sahara Desert somewhere. Now you're blindfolded, you're going to land, reach down and pick up that single grain of sand, and you've got it right. And then we repeat the process. You have to do it twice. That's that number. So that's pretty small. And that's only a 29-member sequence. Well, hey, maybe time plus chance could do something like that. Well, if you had a prebiotic soup trying to assemble this 29-member protein, if you will, bouncing off each other, making new 29-member sequences 1,000,000 times a second, how many years would it take in order to come up with this sequence? 1 billion years? How about 1 billion billion and then 1 billion times that many billion years? You think, oh, it can't be that complicated. Well, it is. This is very unlikely to occur by chance, okay? So it's a very, very small probability. Now, this is our ribonuclease again, the same one you looked at. 129-member sequence. You've got to have it before you can reproduce. It has to be present before you can reproduce. And this is a 3-dimensional mock-up or computer-generated model of what that ribonuclease looks like. If you change out one of these building blocks, it won't look like this. And the molecule you'll see nestled in there in 3 dimensions, fitting just perfectly, will not fit, and the protein cannot do its job. Very specific. You've got to get it right the first time. Now let's look at the prebiotic soup and try to come up with something like our ribonuclease there, which we know is necessary for life. It turns out that the building blocks of life, the amino acids, come in left and right-handed pairs, okay? In stereochemistry, they come, we call it left and right-handedness. Suffice to say that outside of biologic systems, if you just make amino acids in a test tube like we did in the first experiment, you get half right-handed and half left-handed. In your body and mind, in all living systems, you only get L forms. Only. Okay? So if you may want to make a protein, you can only have left-sided forms. So everyone is 50% chance. Now, a peptide bond, which is the way the building blocks hook together, and all proteins are built, the chemical chain of which you saw in the previous slides, is not the only way that amino acids can be put together. it turns out you only have a 50% chance of getting the bond you want. So at every point now in this 100-member sequence, we're down to 1/4 of the chance of what we're looking for. Now, let's assume, which is a big assumption, that in the prebiotic soup you have only the 20 chemicals that you want. That could never happen, of course. But let's just say that so we can spit the numbers out. In the prebiotic soup, you've got the 20 building blocks I need to build me, okay, or our ribonuclease, and we're going to let them mix around and bounce into each other. And we'll imagine that we have a protein about 100 building blocks long, like our ribonuclease, which we need for life. Well, the probability gets really small, 4.9 times 10 to the 191st. Now, it's going to be hard to get our hands around that number without help. So we have to go to the Milky Way, okay? This is 60 grams of pure sugar. I love it, okay? How many atoms are in this candy bar? Oh, about 2 times 10 to the third. It's about 1/3 of a mole, if you know what I'm talking about, okay? And that's a pretty big number. But remember, atoms are really, really little, okay? It turns out that this Milky Way bar, this Milky Way cannot really achieve our purposes to get our hands around a number as big as 10 to the 191st. We need this Milky Way to do it. How many atoms are there in this galaxy? 10 to the 65th atoms in the galaxy. Now, atoms now, not planets, stars, or anything else. We're talking about little bitsy bits. Okay, now, we've got our blindfolded gentleman who was real lucky in the Sahara Desert. He picked out those 2 red grains of sand, right? He's got to go to the Milky Way galaxy 3 times in a row and pick out the one atom that we set out ahead of time in order to come up with this one protein that we need. Chance is limited in what it can achieve. We've got a problem getting from the prebiotic soup to proteins because the amount of information found in even the simplest protein exceeds the probabilistic opportunities of the entire known universe. We've got another problem too if we want to get to life, because in order for life to occur, it's estimated that the very simplest cell, which is simpler than the bacteria that you know about, needs about 2,000 of these enzymes or specific proteins in order to live. Why is that? Because the proteins need to interact with each other in order to help us digest that Milky Way bar, for instance. What we're going to look at next is the sequence of enzymes necessary in order for you to eat that Milky Way bar and get some energy from it. This is a little piece of the Krebs cycle, which is used to utilize glucose or carbohydrates. All the blue words are enzymes necessary just to help you metabolize that Milky Way bar. They have to work together. They have to be in the same place at the same time. And they have to be at the right temperature, pH, and everything just right for you to eat the Milky Way bar. This is what it takes. So I think we've got a problem getting not only from the prebiotic soup to the proteins, but also getting from the proteins to metabolic pathways, because you see the amount of complexity necessary in order to just digest something as simple as a candy bar. Chance can generate non-complex specific information or unspecified information that's complex, but chance cannot and does not generate complex and specific information. That is a hallmark of intelligent input. There are some limitations then to what time plus chance can achieve over time. And as we look at biological machinery, we have to ask ourselves, is that a product of time plus chance, or do we see the hallmark of design that is complex and specific information? When we see it, can we recognize it as design?
Who are you people?
Sham. Danny, I want you to come with me right now, okay? Show me your room.
listen to me very carefully.
Listen to me very carefully. If you look at Arnold's arm under the skin, does it bear the hallmark of complex and specific information? Is it reasonable to think that that nuts and bolts assembled itself by chance? Is that the best fit for what you see? Or is it what it appears to be? That is evidence of design. And in medical school, as we take the skin off a real arm and look at the bones, ligaments, and muscles underneath, we see something far more complex than Arnold's arm here. Yet we don't think twice about assigning that to chance. Why is that? We'll find out maybe later. Now let's look at a second stumbling block to the naturalist explanation for origins, and that's something called irreducible complexity. And I'm indebted to Dr. Michael Behe, who's a professor of biochemistry at Lehigh University. I've borrowed liberally, I'm afraid, from his diagrams concerning explaining this topic in biology. Irreducible complexity, he would say, is a lot like describing a mousetrap, because a mousetrap might come in 5 parts. You've got a platform, a spring, a catch, and a holding bar, right? And if you know how they work, they can really do a job on your finger. But if it's missing any one part, how well does it catch a mouse? You've got 5 pieces here. If you have 80% of a mousetrap, can you catch 80% of the mice? Are you 80% efficient at catching a mouse, or do you get 0? The point of this illustration will be that you have to have all the pieces together, or else you don't get anything, because irreducible complexity states that this organization of many parts is present. Each part may not be useful individually, and the functional whole is greater than the individual parts. The catch, the spring, the platform aren't much good by themselves, but put together, it achieves something. Each part is necessary for the whole to function. You're missing one part, you get not 80% of a mousetrap, you get no part of a mousetrap. And there's an apparent purpose to the whole, isn't there? It catches mice. Put cheese on it, it catches a mouse. Now, anybody have this game at home? Okay, so you recognize it. You see the pieces there? Do you get any indication from those pieces that you could catch a mouse with this thing? In fact, I think you have to look at the directions pretty hard to make it work, right? The interesting thing is that at our house, with 3 active kids, we can play the game one time. I think this is the one time you can get it to work. Why is that? Because once you lose one of those pieces, can you play the game again? That's it, okay? But we got it out of the box, and we got it working this one time. Let's see what happens. So, we've got the mouse, okay? You've got all the pieces there, but it's interesting to note, not only do you need all those pieces together, but when you're done with catching the mouse one time, is the mousetrap ready to catch another mouse? What has to be put into this game in order to play again? You have to put the ball back up on the stand. You need some information, intelligent information, put back into the system. This is something that we see with irreducible complexity. Now, what does this have to do with our topic tonight? We have to understand what Darwin actually said about an origin of life with no designer. One of the things that Darwin said, and these are some of the points that will bear on this irreducible complexity concept, is that species change over time. That over time we develop capabilities that we didn't have before, that we can increase in complexity. It's one of the things that can happen. That variations within a species or group of animals are caused solely by random mutations in the genetic code, okay? That DNA that we've been looking at that codes for the proteins has to have information in it first before the proteins are made. Otherwise, you can't pass that information down to your descendants. Variations within a population allow natural selection to select organisms that have a better chance of survival. For instance, suppose you're the hyena. What would you like to have? Big lungs, stronger legs, right? We've got to get away from this lion. If you're the lion, you'd like to have stereoscopic vision, big claws, right? And these are the things that are necessary for survival. This is called natural selection. If you're the hyena with short legs, you're going to have a problem. If you're the lion that has no eyes, you're not going to make it. Okay? So this is what Darwin says. And this is how simple life has become complex life. Now, Darwin knew that there would be some problems with this idea. And one of the things that he recognized immediately was that a complex organ, such as an eye that existed, which could not possibly have been formed by numerous successive slight modifications, would break his theory down. Okay? In other words, an eye would have to occur in gradual little steps in order to allow his theory to have some plausibility, right? Because if it happened all at once, it looks too much like a miracle. It has to occur in little bits and completely by chance. So we can imagine that a coherent light-sensing array could arise by chance and focus the beam of photons exactly on it. Okay, let's grant that. But what good is 5% of an eye? If you have an eye that's only 5% there, it doesn't function, it's of no use to that lion in catching the hyena. You have to have a functioning organ in order for natural selection to work on it. There's something else that Darwin didn't know, and that has been borne out by research in molecular biochemistry, and that is that there's challenges at the level of the nerve cell itself. So forget the eye for right now. Let's just talk about a nerve cell that can sense light. Most of the nerve cells in your body do not have this capability to sense light. What does it take? What's the mechanism to allow a nerve cell to sense light, right? If you want to be a lion with an eye, you've got to have a nerve that senses light. Well, it looks something like this, and we won't go through the specifics except to say you need these two proteins right next to each other to sense the light. They change their three-dimensional structure in order to break down a third compound, which then acts on an ion channel in the membrane of the cell. Every block that you see up here is another very complex long protein, okay? Now, having gotten this far and letting the sodium into the cell, we get the cell to depolarize or fire. It makes an image on the back of your brain. So that's all well and good. But now we're like the mousetrap game after we turn the crank. It's only good for one time. How are we going to get those proteins that have already fired, so to speak, back in their original shape so that the nerve cell can do this again? Well, good thing these other proteins are ready to go in the red now to replenish some of the depleted proteins from before. And good thing they were just adjacent to the proteins necessary in order to sense the light. And we can end up right back where we started. That all occurred by chance, by the way.
The central dogma of molecular biology, as first stated by Francis Crick, asserts that information flows from DNA to RNA to protein. Information never flows from protein back up the line.
Okay, the information has to be in the DNA first. This all happened by chance, so the DNA had to have all these mutations or changes by chance, coding for that number of proteins all together, or else the nerve cell doesn't sense light. How much of a mousetrap is that? You have to have 100% or none. Nothing that happens to the body turns around and affects the germ cells. Characteristics developed during an organism's lifetime simply cannot be transmitted to offspring. The proteins in that nerve cell that say you got half of them by chance can't tell the DNA or the genetic material back at HQ, hey, you got half of an eye here, hold on to it, and then keep working on the rest because we'll eventually get there. There's no purpose, remember, and it can't hold on to these things unless it does something in terms of natural selection. Irreducible complexity says that the smallest jump that you can take is not jumping over a puddle, but a leap across the Grand Canyon. Structural proteins are coded for in DNA, and DNA sequences are randomly generated. DNA is stupid. This is something I learned in school. DNA is stupid because it cannot know when it's got a successful outcome. It can't know when it's got half of an eye. Remember, for Darwin's theory to work, it's got to be numerous, slight, successive modifications. Anything bigger than that looks too much like miracle, and we can't have any of that. Natural selection. We'll introduce Richard Dawkins. If you have a chance to read his books, I'd advise you to do so. He's a biologist from England who's a strong spokesman for naturalism. Very brilliant, interesting books, but the conclusions he comes up with, I think, are worthy of scrutiny. Natural selection, the blind, unconscious, automatic process which Darwin discovered, and we know is the explanation for the existence and apparently purposeful form of all life, has no purpose in mind. It has no mind and no mind's eye. It does not plan for the future. It can't save half an eye and expect expectation of the rest. What is. There's no direction. There's no vision, no foresight, no sight at all. It's the blind watchmaker. Now, we'll move into an area that's a little bit closer to home for me. What happens when you're cut? Anybody know what happens when you're cut? First you bleed, and then next you stop bleeding. And what we're interested in seeing is how much bleeding we actually get when we open some skin up and take a look at what's underneath. Now, the patient's head is up to your right. Even if we divide that this is the breastbone right here in the front, this is how you get to the heart, at least the way I do. And you can see that right behind that breastbone, even if we pull that apart, you don't get much bleeding, do you? So when you get cut, you bleed, but then you make clot, right? Because there's proteins circulating in your blood that recognize the disruption of the blood vessel. As soon as you get cut, it happens right away. These proteins organize very quickly into a clot. Now, having sat through this much of this, do you think that's a very complex process, a very simple process? Okay, she's laughing already right here. This is just a small part of the coagulation cascade, and we're not going to belabor the whole thing except to tell you that each one of the words up there represents a separate and distinct protein that does a part just like that mousetrap game does. It doesn't do anything by itself, and you can't recognize it as doing a part of what the whole has to do, which is to make a clot. If you're missing this particular protein, factor 8, anti-hemophilic factor, then you have hemophilia. You know what happens to those people. If you're missing this protein, Christmas factor, that's factor 9, you will have bleeding that will not stop. Okay, and it will cause the death of the organism. The end result of all these enzymes down in this cascade is to get a strong fibrin clot, something that will trap platelets so that you don't bleed. So you'll be like that lucky volunteer who was getting their chest open and have their bleeding stop just like it should. Now, if you get the blood clotting started, you've got to find a way to make it stop. Because if you start this cascade of coagulation, what's to stop it from coagulating your whole body, which happens sometimes in the lab, not to people, but sometimes in the lab. Circulating blood doesn't seem to clot. There must be some way to keep circulating blood from clotting, and indeed there is. This protein called plasminogen in the green here. Plasminogen is the precursor of an enzyme that can break down the fibrin clot. This is plasminogen. You've got to have it in order to break down the clot. Everybody has it. You wouldn't be alive if you didn't. Bad news is it's 792 amino acids long. Now, you saw the odds of having a 100 amino acid sequence. We're talking about 792. You know, all the proteins on that slide are about this size. I could just find this one easily to show you. And in fact, that plasminogen has to be acted on by a second protein called TPA, which we give all the time in the cath lab or the emergency room in order to stop heart attacks. TPA, tissue plasminogen activator, looks something like that in schematic form. In 3D, it looks like that. Very specific. It's got to work. When it comes from the lab, which it can be made in the lab, I'm not going to pay the $5,000 for this vial, or you shouldn't, unless you get exactly that. Because if you don't get that, it's not going to work. The plasminogen is cleaved by the tissue plasminogen activator into an active plasmin. It does something like this that breaks down the fibrin clot that you've got. This is an example of irreducible complexity. You've got to have it all, or you get nothing. So the coagulation system shows some hallmarks of irreducible complexity. These are stumbling blocks to achieving something by natural selection, because any differences within a species for natural selection to act upon has to have a wholly functioning system. So it comes all together or not at all. Huge leaps, too big for chance alone. Mutations, remember, are random with respect to the needs of the organisms. Mutations don't occur because you want them to. They are mistakes. Remember, no vision, no guiding force. This is just what is. Okay, now this is also a little closer to home for me. I trained in New York, and we never had lungs as good as these in New York to transplant with. These are good Oregon lungs. Because you can see they're nice and pink. None of that air pollution and smog and so forth. Everything's nice and clean out here, so we love it out here. The job of the heart and lungs is to exchange oxygen and pump the blood around so that oxygen can get to the cells in your body. In my work, sometimes we mix and match these in order to help people who need a new lung or a new heart. In order to do that, we have to have a machine that can temporarily do the work of the heart and lungs. This is a heart transplant patient, feet away from you, head towards you. And the tubes you see leaving the operative field there are part of the heart-lung machine, which looks like this. Now, the artificial lung is that little canister you see right in front of you. It has semi-permeable membranes in it and little microtubules that allow us to exchange oxygen and carbon dioxide. The effective surface area of that artificial lung is about the size of a coffee table, okay? About 1 meter to 2 meters squared, depending on the brand you buy. The effective surface area of your lungs, right now sitting in this room breathing air, is about the size of a tennis court, okay? So that you have that much area available for gas exchange. So what we can make is a pour second, but for a few hours it works well enough for us to do what we need to do. The rest of the pump you see here is necessarily complex because it needs to pump back the blood to you at a certain temperature, pH, pressure, and so forth. It needs to be very carefully regulated so you don't have a very bad day at your heart surgery, okay? Now, that is a complex piece of machinery. But we are told by Fred Hoyle, a famous astrophysicist, that if he had a tornado in a junkyard and just let that tornado in there for long enough, time plus chance, that eventually we could get a functioning 747. You know, time plus chance can achieve a lot of things. So we decided to put him to the test. And we don't have a junkyard, but we decided to go to Home Depot. And I know you've all been there. How many line items, that is, how many different items are there in Home Depot? 80,000. We asked the manager, 80,000 line items. So we said, well, that's a pretty good junkyard. In fact, these pieces are ready to go, so we're going to give you an advantage. And we don't have a tornado, but we had the next best thing. And that is, at that time, my 2-year-old son, Nathan. So Nathan goes into the junkyard, and he gets to work the way only he can do. And he's going to go to plumbing, and he's going to help his dad improve on his functioning heart-lung machine. Okay, I needed a heart-lung machine for work, and Nathan the tornado, I want you to go in there over time and make it better. So Nathan goes to plumbing, and you can see he's really got he's got a good set of plans here. Maybe get some help from his older brother. And he'll go to electrical and he'll go to plumbing and find the things he needs to do. What's the point of this? The point is that if we gave Nathan the functioning heart-lung machine that his dad needs for work and gave him time, what would happen to the function of that machine? Inevitably. Is time your friend? No. The moment you've got something by chance that could possibly work, time will act to decrease the organized energy and complexity, functioning complexity of that system. You give Nathan time and he can wreck just about anything, okay? But this is why time is not necessarily your friend in the time plus chance scenario, because over time you're going to lose complexity, not gain it, and he's off to a good start there. Natural processes, then, let's sum up, do not create complex and specific information. Complex and specific information is the hallmark of design. If you go into the desert of Egypt and you dig a hole and find the Rosetta Stone, what are you going to think? How do I find how this occurred by natural processes? No, you recognize it immediately for what it is, the object of design. Natural processes do not create complex and specific information like you'd find in a Rosetta Stone. Natural processes lead to increasing disorder and loss of information over time. Nathan working over time decreases organized complexity, decreases function. Remember, all this has to have a basis in randomness. DNA must create complete, immediately functioning, complex organs, complex and functioning enough to allow a difference in natural selection. The eye has to work. The neuron has to sense light the first time, or else this doesn't work. That's too much for chance to account for. Now, we talked about Dr. Dawkins before. He wrote a series of books. This is a good one, Climbing Mount Improbable. And he's an apologist for the naturalist view. And he says, you know, I agree with you. If you go and look up the sheer face of Mount Improbable with the eye at the top and just chaos down here, how do we get from down here to up there? Well, it looks improbable, but what if we go around the back? If we take very small steps to get around the back of Mount Improbable. Gradualness is of the essence. If you throw out gradualness, you throw out the very thing that makes evolution, naturalism, more plausible than creation, design. But we know that the smallest steps in gradualness you can take are jumps to the moon, not a jump across the puddle in the backyard. Chance cannot get you from here to the moon. Could time plus chance produce the observable biological systems we see today? I would think not. How do we explain the origin of this complex and specific information? Or is it the case that the evidence, science, implies intelligent design? I would put to you that we look a lot more like Mount Rushmore than we do Monkey Head Rock. We're not the only ones, or I'm not the only one, to think that that's the case. Because a neutral observer, or any observer, has to admit the numbers don't add up. Dawkins himself says that it's statistically improbable. I think that's gently understating the case. But the more statistically improbable a thing is, the less we can believe it occurred by blind chance. Superficially, the obvious alternative to chance is an intelligent designer. Now, why did he have to write superficially? Is it because the evidence, just taken at face value, has design stamped all over it? Anybody know who these folks are? Watson and Crick, good. What did they do? Describe the DNA double helix, a landmark in biology. Nobel Prize-winning scientists, both of them. Francis Crick on your right, still very active, writing in the major journals and a major player in the field of science today. He despaired in the late 80s and early 90s when he looked at the molecule he himself described and saw the amount of information present in it, and came to the conclusion that, there's no way this could have happened by chance, not in 15 billion years, not in any length of time, because time is not necessarily our friend. So what am I to think? How did this come to be? I'm at a loss here. Well, he came up with a second theory of how all the information got in our DNA. Anybody know? This is a Nobel Prize-winning scientist now, describer of the DNA molecule. He decided that we came from outer space. Now, it's not a joke. This is called panspermia, and it means that there's an extraterrestrial origin of the DNA information that's in your and my cells. No one laughed when he presented it and published it in Science magazine because of who he is. But look where it's brought him to in order to explain away the amount of complexity in every cell in your body. Having chided the theologian for his reliance on myth and miracle, science found itself in the enviable position of having to create a mythology like panspermia of its own. Is it the evidence that's driving us to that? Or is it something else in our thinking that limits us in terms of seeing intelligent design, because we can see that there is evidence in empiric science for design in natural biology? Well, you have to ask yourself, what is science, maybe? And like most things in America, when we have a question to answer or some dispute to settle, what do? We sue each other. Perfect. That's what we do. So ACLU versus Arkansas in 1981, Judge Overton was forced into the position of having to tell us what science is. I'll just focus your attention to the last two, because this is germane to the remainder of our discussion. Number 4 down there, the conclusions of science must be tentative. What do we mean by that? It means that anything that you pronounce as science must be able to be retracted if it's later proven wrong. You can't make absolute statements that can never be tested. Number 5, it's falsifiable. That is, you have to be able to test it. There has to be some experiment you can do that will allow you to verify whether this is in fact the case. Let's look at some of the statements of some of the leading scientists today that's taught in our classrooms. Modern science, this is William Provine at Cornell, still very active. Modern science directly implies that the world is organized with mechanistic principles only. There are no purposive principles whatsoever in nature. Modern science directly implies there are no inherent moral or ethical laws, no absolute guiding principles for human society. Statement of science? What do you think? Human beings are marvelously complex machines. I would agree with that. But the individual human becomes an ethical person only by heredity and environmental influences. That's all there is. You're just a bag of chemicals. And we must conclude, therefore, that when we die, and that is the end of it. Science? Or is that a statement of metaphysics and philosophy? Well, let's see where this drives us to. if we really are just the product of the prebiotic soup, then at the bottom of it all, there really is no good or no evil. That's an illusion. There's no purpose. There's nothing but blind, pitiless indifference in the universe. DNA neither knows nor cares. Your genetic material just goes on through history. It just is. We dance to its music. The universe is all there is and all there ever will be. Is that a tentative statement? Is that a falsifiable statement? I would put to you that this is not a statement of science, but a statement of metaphysics or philosophy and religion made by a scientist. Now, I'm the first one to value empiric science. We use it every day in my work. It's an important thing to do, to be able to measure things, predict. But we have to be able to separate the philosophy from the true science that allows us to achieve what science does today. So having all these really bright people know so much about nature, what is it that keeps us from recognizing design, which is right in front of us? It's interesting that in this very telling quote, I want atheism to be true, and I'm made uneasy by the fact that some of the most intelligent and well-informed people I know are religious believers. It isn't just that I don't believe in God, and naturally, of course, I hope that there is no God. I don't want there to be a God. I don't want the universe to be like that. Now, if you're a scientist starting out from that, how are you going to see the evidence when it's put before you? And secondly, if we don't want the universe to be like that, does that really affect reality? If I don't want it to be a certain way? That's a kind of unreasoning faith, isn't it? Dr. Dawkins himself says that faith, being belief that isn't based on evidence, is the principal vice of any religion. Now, he was speaking of people who might approach design as a reasonable, plausible explanation for origins. Faith, being belief that isn't based on evidence, is the principal vice of any religion. I would say that the shoe is on the other foot, because it's difficult to see how the evidence actually squares with naturalism. Where does this faith come from? I think it's seen in the previous slide, because design gives us a good view, a good fit for explaining nature through a molecular biologist's view. Now, Lewis Thomas was the chancellor of Sloan Kettering Memorial Hospital in New York, probably the leading cancer institute in the United States, maybe the world. Great giant of science. We had to read his book as part of our senior year in medical school. It's called The Youngest Science. It's a good read if you have time to read it. But he said this: biology needs a better word than error for the driving force behind evolution. I cannot make my peace with the randomness doctrine. I cannot abide the notion of purposelessness and blind chance in nature, and yet I do not know what to put in its place for the quieting of my mind. You see what he says here? You know, I see the evidence there. It doesn't quite fit together. But there's also something else. Besides just the evidence, there's something inside me that tells me I'm more than just a bunch of chemicals. There's something in the human condition that's not described just by chance atoms bouncing into each other. I can't abide the notion of purposelessness. I rebel against that, but I don't know what to put in that spot. Many of you are familiar with Pascal and what he said. He said there's a God-shaped vacuum inside every man, a need that only God can meet. Some of the evidences we look for tonight tell us that God is a God who is not silent, that he's revealed himself. Not only is he out there, but he's communicating with us. How does he do that? One way that God has done that is through what he has made. And we see that through some of the examples we've looked at tonight. Through creation, through what's been made, God has revealed himself. I believe that God has also revealed himself through his word, through a specific revelation that tells us more about him. We know a little bit about God from his creation. We know that the heavens declare his glory. We know that we are fearfully and wonderfully made. We've seen a little bit of that from the examples of molecular biology. Inside every cell in your body is that portrait of God, if we just look there. But he's also revealed himself in his word, through the living word, through his son, Jesus Christ. And Jesus makes these claims for himself, and this is God revealed. I am the bread of life, satisfies us. I am the light of the world, shows us the way. I am the way, the truth, and the life. These are the claims that Jesus makes for himself through his word. Why is that important? Because as we come full circle now and say, where did I come from? If I'm just chemicals from the prebiotic soup, then who I am really doesn't matter that much, because identity is just these molecules bouncing around in my head. Why am I here doesn't really matter, because the emotions that I have, the love for my family, the joy at being able to be good at music or enjoying music, those things are just an illusion. They're not really real. They have no meaning. Where am I going? To the same place you came from. Just chemicals wandering through the universe. But if you came from a personal beginning, if God created you, then the who am I becomes a very different question, isn't it? Who you are is a person designed by God to have a relationship with him. Why are you here? To enjoy that relationship and know your Creator and have meaningful relationship with each other. And where am I going? Well, that's really the question for all of us.